All right, in this final section of Unit 7, we are moving on naturally to the area between two curves, having already looked at definite integrals, the way to compute them by hand, way to compute them on the calculator, what they represent in terms of area under a single function. So we are on to section 5.11 of the IB SO Analysis and Approaches syllabus. Very simply put, area between curves. So this is a nice extension from what we've done and should flow pretty nicely to complete this first unit of integration. Okay? So we're thinking about this area A on this little picture we've got drawn here, this area colored in green. And what's different about this from the previous section is this area is not made with the x-axis, it's made between these two curves that are blue and red. Okay? So it's very simple to see that this area A would be found from the area from A to B, and it would be the subtraction of these two functions. So it would be f of x minus g of x dx for that area. Okay? Now why is that so? What if I thought about the integral from a to b of f of x dx? Well, that would give me the area under the red function all the way to the x-axis. So that's what I roughly shaded in green there. Okay? If I then subtracted from that the integral from a to b of g of x dx, that's the blue function, that would be subtracting this area that I'm kind of coloring in, this purpley color that when I put it on top of the green, it kind of goes this very dark kind of black color, but you get the idea. Okay? If I subtract those two areas, I'd be left with that little thin strip in the middle, which is exactly what I want. Okay? Well, this subtraction of integrals is a property that we've seen before, that we can combine it into one single integral like we have over here. Okay? So that's the logic behind what we're doing. We're just going to go ahead and do it today, but we should have a little general understanding of why this works. Okay? Now, obviously, the condition for this to work is the f function has to be on top of the g function. That red curve has to be on top of the blue one on the area we care about. Okay? So how do we say that mathematically? F of x has to be greater than or equal to g of x on the interval a to b. Okay? If we want to generalize this a little more, we can put it in words. This is the integral of our top function. Okay, that's a very non-mathematical way of saying it. Top just means the one that's higher up. Top function minus bottom function on our interval. Okay, so it's just the function on top subtract the function on bottom. Okay? And this is not in the booklet, which is why we really want this connection about why it works to be strong, so that we can reproduce it again on those exams when we don't have any resources to help us. Okay? So we'll begin no calculator, and then we'll get onto some calculator problems as we go through this class today. Okay? So the first problem is straightforward. It says find the area of the region between these two graphs on this interval. Okay? So the first thing we need to figure out is which one of these functions is on top of the other one. So we've got a standard parent function cubic. We know a little bit what that looks like. It snakes through the origin, okay, and it has this kind of cubic shape. Okay? The other function is a parabola, okay, that is the quadratic x squared minus x. Okay? And if we go ahead and factor that up, we can take out a common factor of x, and it'll leave us with x minus 1. So we know it has zeros at x equals 0 and x equals 1. So if we put these zeros on our graph, we know our parabola is crossing at x equals 0 and x equals 1, and we know it opens up, and it's not going to grow as fast as our cubic function, so it's going to sit under, that's a terrible parabola right there, it's going to sit under the cubic function right here. Okay? So what is the area we're trying to find? We're trying to find the area on the interval 0 to 1. So it's this little chunk of area, I'll color it in green right here. So it's this piece that goes under the x-axis, but also above the x-axis. Okay? Now the great thing about this subtraction formula when we do the area between two curves, we don't have to worry about areas above and below the x-axis as long as we stick to that idea of top function minus bottom function. Okay? So this green area will simply be calculated by the integral from 0 to 1 of the top function minus the bottom function. Well, the top function is the cubic function, the bottom function is the parabola, so we just need to go ahead and subtract these two inside the integral. Okay? Now we could break this into separate integrals, but it's actually a lot easier if we simplify the algebra first and then just integrate once. Okay? So we can take the antiderivative of this. It's x to the 4 over 4 minus x cubed over 3 plus x squared over 2. Our limits will go on the back of this integral. I don't know why I made them 0 and 3. It's 0 and 1. We'll apply our evaluation theorem to substitute those in. Okay. This is 1 over 4 minus 1 over 3 plus 1 over 2. Okay. All the second parenthesis zeros out as all of those x's turn to 0. And you have a nice little fraction problem here where you're trying to put everything over a common denominator, which I think will be 12. So we'll put everything over 12. This will be 3 over 12 minus 4 over 12 plus 6 over 12. Adding those together will give us a result of 5 over 12. Okay? So that little area we shaded green has a value of 5 over 12. Okay? So hopefully it's really just one more step than the previous stuff we've been doing in the other videos. It's just that extra step of subtracting these two functions to get us going rather than just integrating one function. So we'll do a little more here, no calculator, and then we'll bring in the calculator. Okay? So in this question, we're asked to find the area, and we get this word we've seen before again, enclosed by these functions. Okay? So the difference here is we're not given limits or bounds for our area. We have to find those bounds based on this idea of the area being enclosed. Okay? So we'll graph these two using the graph paper here. We've got a linear function which should be easy to graph. It's got a y-intercept of 1 and a slope of 2. So we can draw that nicely on our little piece of graph paper right here. I'm going to try not to use my straight line tool. Looks something like that. So we want to go ahead and graph this parabola, but the points we really care about between this parabola and this linear function are the intersection. Those are going to give us the bounds for our definite integral. So we could do the vertex and the axis of symmetry and the zeros and all those things for this parabola, but let's focus in on the bits we want. We want those intersections. Okay? So those are found by setting these two functions equal to each other. You can then go ahead and solve this by subtracting off the 2x and subtracting off the 1, giving yourself a quadratic, which, if I was nice, I believe factors x minus 1, x minus 4. So we have intersections at x equals 1 and x equals 4. So we can find those on our straight line, and that's all we need. We know this is a parabola that opens up, so it's got to come through these two intersection points, giving us this little sliver of area that we're interested in finding right here. And what we're really using this picture for is to see which function's on top and which function's on bottom. Okay? So it's pretty clear to see on that little green region, the red is bounding on top, the blue is bounding underneath. Okay? So our area will be found by the integral from 1 to 4 of 2x plus 1, that's our top function, minus our parabola right there, the x squared minus 3x plus 5. Okay? Again, we will simplify down first rather than integrating first. We want to combine as many like terms as we can to give us as few pieces as possible to integrate. Okay? So if you combine this, you should end up with negative x squared plus 5x minus 4 dx. And this parabola should look a little bit familiar. Okay? It looks very similar to the one we got when we were solving for the intersections. Okay? The only difference is it's the negative version of that. Okay? Now, why is that? Well, we were solving right at the top, setting these equal to each other, and we subtracted the 2x plus 1 over to the right side. All we're doing when we're building the integral is subtracting the x squared over to the other side. So it makes natural sense that these are the negatives of each other. Okay? Now, in the interest of time, we've got this integral set up. We're going to go ahead and give this to the calculator, though in a non-calculator paper, you would obviously find the antiderivative and apply the evaluation theorem like we've done many times. Okay? So we will hand this to our calculator right here. Let's go ahead and get that up. We will just hit the scratch pad for this. Okay? We'll grab our integral template, and our integral is the integral from 1 to 4 1 to 4, negative x squared plus 5x minus 4, put in the dx, and our calculator will give us this value of 4.5, or if you prefer fractions, 9/2. So obviously I've skipped a lot of the manual work there just to save time on this video, but you should go ahead and do that work to check that that comes out correctly. All right, the second problem allows us to use a calculator. It's very similar. It wants the area bounded by these curves, so again, it's not giving us limits. Okay? Now, the advantage of having a calculator here is we can use the calculator to both make the graph, do the integral for us, or maybe even both at the same time. Okay? So let's take a look at this. Let's get this graphed up. So we've got e to the x minus 5. We should know what this looks like. It's a exponential function shifted down 5. Looks like that. We'll hit tab to put in our second graph. 3 minus x squared, that's a parabola that opens down. Okay? And you can find the intersections here and then set up an integral, or if you have a TI Inspire, you can actually just go menu, analyze graph, and then this bounded area option. Okay? It'll ask you for a lower bound, and if you get close enough to the intersection point, it'll actually put a little dot there and you can just click. Okay? So this is one of the awesome features of the TI Inspire, is you can do this bounded area all in one go and simply get out an answer. Now, just writing that answer down on an IB exam is a little high risk, so I would highly recommend you at least set up the integral before writing down that answer. Okay? So our top function is our downward facing parabola. We're subtracting our exponential, and this integral comes out to be 21.6. If we really want to get those points of intersection to complete our definite integral, we can absolutely do that. We go analyze graph, intersection. So it was from negative 2.82. That was our lower bound. We'll do it again. Analyze graph, intersection. Yeah, upper bound was the x value, so 1.66. Okay? So on an exam, I would recommend showing that work. Maybe you don't draw the graph. If you just go with the answer and it's wrong, you don't really have any fallback for those method marks or any evidence of what you were actually doing there. So, quick little summary of this area between curves. Okay, there are some more advanced scenarios where this top function, or this top curve and the bottom curve, these guys can actually switch within our region. So you can get an intersection within your region where the two tops and bottoms switch. Okay? If this is the case, we really need to find those intersection points. And then we're going to have to set up multiple definite integrals and add the areas. Okay? So we're going to have to set up definite integrals for each area. And then we'll obviously add those resulting areas. So we'll close out Unit 7 by looking at an example that does this. Okay? Find the area of the region bounded by these curves. Okay, these curves are a little more complicated. We're told we can't use the calculator for the intersections, and we can decide if we want to use it for the integrals. We'll probably use it for the integrals just to keep things short on this video, but you're welcome to do those integrals by hand if you want. Okay? So we know the intersections are found by setting these guys equal to each other. So x cubed plus 2x squared equals x squared plus 2x. We obviously solve this by getting all the terms to one side. So that would be x cubed plus x squared minus 2x equals 0. We have a common factor of x here that we can take out. And then we can factor away with our x plus 2, x minus 1 here, giving us our three intersections of 0, -2, and 1. Okay, so now that we have the intersections, we can use our calculator to figure out what the graph looks like. Okay, that will allow us to see which function's top and which function's bottom on all these different regions. Okay, so we'll head over to the calculator for that. We'll get ourselves a nice little graphing page. Okay. We will graph x cubed plus 2x squared. Should look like that cubic right there. And our second function, x squared plus 2x, will look like that. Okay. We see our three intersections, one here, one at the origin, and one over here. And then we can see our two regions right here. We've got this big region and then this little slither over here. Okay. So I'm going to screenshot that so I don't have to draw it myself because I'm kind of lazy. I'll grab a screenshot of that. Bring it into our working document. There it is. We'll resize it. And we'll begin setting up some integrals here. Okay. So we have two areas. The first one goes from -2 to 0. The second one goes from 0 to 1. I'll color the first one in green. That would be this area right here. And then our tiny little area, I'll do it in yellow. That's this little slither right in there. Okay. So the integral we need for the green area, let's get ourselves a little workspace. The integral for the green area, we'll call that A1. A1 will be the integral from -2 to 0. Our top function would be the cubic, so that's x cubed plus 2x squared minus our parabola, x squared plus 2x dx. Our second integral we'll call A2, that's the little yellow area. That will be the integral from 0 to 1. And in that case, we actually have the parabola on top because they've switched. So it's parabola minus cubic. Okay. But we can hand both of those integrals to our calculator or simplify the algebra. I'm going to go straight to the calculator at this point as we look to get these done as quickly as possible. Okay. So we can do two bounded areas here. No problem with that. Or we could use the integral template. Okay. We're going to click those areas on there. We'll get 2.67 for the first one. We'll run another bounded area calculation again to get the little yellow area. And again, the TI Inspire allows us to click real quick to those intersection points. So we get these two values, and our final value is found by just adding these two guys together. Okay? It should make sense that one of them is quite a lot bigger than the other one, just given the graphics that we're working with here. So our final area will come from 2.67 plus 0.417. So total area 3.09 if we stay to three significant figures. Okay. Again, we could get that by hand, probably more of a fractional answer, but we're just using the calculator to speed up all the integrals for us. Out of interest, you can also, I believe, do this all with one bounded area. So if you are on your calculator, okay, let me see if I can delete these. It doesn't look like I can. I can just go Menu, Analyze Graph, Bounded Area, do one bounded area, and I can get that same value out, 0.308. It's obviously got a little rounding error on my answer that they don't have on theirs. So you can just do one big integral to get that as well. All right, that completes everything on our first unit of integrals. Please stay tuned for the second unit, which will do more challenging integration techniques as well as applications of integrals, including kinematics. Thank you for watching.